So before we go into the depths of the lab, we're going to give a little bit of background information on spring motion. The back and forth or oscillatory motion of a mass on a spring is called simple harmonic motion. Simple harmonic motion follows Hooke's law, which states the force needed to extend or compress a spring by some distance is proportional to that distance. Now, the motion that repeats itself regularly is called periodic motion. Now, when it completes one entire repetition of this motion, that is called the cycle. And the time it takes to complete the cycle is known as the period. The equilibrium point within simple harmonic motion is where no motion is observed, as the force pulling the mass down is equal to the restoring force pulling them back up. The period t can be calculated knowing only the mass and the force constant by t equals 2 pi times the square root of m over k. And the frequency can be found by frequency equals 1 over the period. The maximum displacement from equilibrium is known as the amplitude, which is represented by x, and the acceleration of the spring can be found by a equals negative 2 pi frequency squared times the amplitude. And if one were to increase the mass on an oscillating spring system with a given k, the increased mass will provide more inertia, causing the acceleration due to the restoring force F to decrease. And this is vice versa, so this is all in application to the Hooke's law. Now, the way the team went about deriving the spring constants was that we applied Hooke's law, the force equals negative spring constant times the amplitude, to calculate the spring constant, which acts as the restoring force. And the process, we started with that Hooke's law, and then we rearranged it with simple algebra for it to be equal k equals force over the amplitude, and then the spring constant was equal to the force, which is mass times acceleration in this case being gravity, over the amplitude. Now the team assumed the value of g to be negative 9.81, but throughout these calculations we only included the magnitudes to keep the spring constant positive. And within the table we could see the various masses that we had hung at the end of the springs, the amplitude of the oscillations observed, and the spring constants that we had calculated with the standard deviations.
Okay, so there were 500 grams put onto a 50-gram weight hanger connected to the bottom of the spring being elevated above the ground. Once the spring was at equilibrium, it was released and the oscillation began.
These are the position, velocity, and acceleration versus time graph for the motion of a red spring, and the attached weight for it was 550 grams. The tracking camera provided us with the data through a CSV file in Excel, and the data provided by that was used to create these graphs, and the period and frequency were provided from that.
For this trial, there were 765 grams placed onto a 50-gram weight hanger connected to the bottom of a spring. When the weight was dropped from equilibrium, it was obvious to the eye that the springer had a larger spring constant due to the smaller amplitude.
These are the position, velocity, and acceleration versus time graphs for the motion of the green spring, which had an attached weight of 815 grams. And the same procedure was applied as the red spring to utilize these datas. And the difference between that and between this one and the red spring, is that it has a smaller amplitude as seen by the position graph, meaning it has a higher spring constant.
For the last trial, there were 900 grams placed onto a 50-gram weight hanger attached to the bottom of the white spring. Just from looking at this oscillation, we could see that it was closest to the 1 second interval that was needed. It is also noted that this spring had the highest amplitude.
Finally, these were the position, velocity, and acceleration versus time graph for the motion of the white spring, which had an attached weight of 950 grams. And the same procedure was applied again, just like the previous two oscillators. And the white one seemed to have a period and a period of 1 second, and a much higher amplitude, which was the objective of this lab.
The white spring is best suited for the clock. It is nearest to the 1 second interval with a frequency of 0.99 periods per second. The red spring had a frequency of 1.0 periods per second, and the green spring was found to have a frequency of 1.43 periods per second. With the new information that was discovered, we concluded that the white spring would be the most suitable and accurate and efficient for a clock.